Alright, hell yeah. Before you is a masterpiece of simple geometry and how to do kind of harder problems, but just with confidence. And so that's what you'll learn in this video. Right now I'm just going to go over the quick answer. And in this process, we use this idea that if you know two things about a right triangle, you know everything about it. And we use the concept of like, hey, if the problem says, hey, this height is going to be the square root 2r, we could work from that solution back to this dimension, you know what I mean, maybe of this triangle. So, hell yeah. So we have a balloon, and when you're looking at it from the ground, you're seeing an angle of 60 degrees from point to point. That's the idea of subtended. And after this, we'll show you what the problem statement says. And then it also says that the center of the balloon is 45 degrees from the ground. Okay, hell yeah. So I did in the video is I said, hey, if I know this side of this triangle, this is a right triangle, and I know this angle is 45, I know everything about it. So right now I know this side and that side. Cool. So let's move on to another right triangle. I'm going to say, hey, this and this is horribly drawn because this tangent, this should be a right triangle right here. Any line, radius from a circle, and this is a tangent to the circle, should be a 90. So we have a right triangle. These are the two components. This is the hypotenuse. I just said that I know this side, and so I know this side and this side of this right triangle. I know everything about it. So I know this angle, and I know this side. Sweet. And cool. And if I didn't know the radius, well, maybe I knew that this angle of 60, maybe I knew that it was evenly split 30 and 30. And from that perspective, you can prove that also in reverse. How do I know that these two angles are the same? Let's do that. And I think I can do that right now. So I'm going to say, hey, if I knew this angle, you know, it's kind of doing the opposite. If I knew this angle, I do know this radius. And so, hell yeah, I know two things. I'm just going to say I know two things about this right triangle. I know everything about it. So I for sure know this hypotenuse. Cool. And if I knew this hypotenuse, well, I know this side and the hypotenuse. So I would also know everything about this right triangle, which would be the angle and this other side. And if this side was the same as that radius, for sure. I think that's fairly accurate proof that both these angles are the same. All right, so let's run through kind of the fast solution. If I start at this radius, and this is my 90 degrees right triangle, this right triangle has this angle of 30. I'm going to draw some sun-shining rays. This is the sine component. I want the hypotenuse, because then once I know the hypotenuse, then I can get this side of this right triangle. This hypotenuse is going to be this component, and we talk about this in depth in the video. And we're going to divide by sine 30. And you can do this on the fly after you watch this video because, hey, sine 30 is a proportion, it's a number between 0 and 1, it's less than 1. Taking this smaller side, dividing it by a number less than 1 gives me that bigger hypotenuse. Hell yeah. If I take this bigger hypotenuse, well, now it's straightforward because, you know what I mean, if I see that this is the angle 45, this is the sine component, so this hypotenuse times sine 45 is this height. And hell yeah. So we got r divided by 1/2. Sine 45 is square root 2 divided by 2. You can remember this just because you should know this is decimal, 0.707. Where does that come from? Double it. It's 1.414. Oh, hell yeah, this is square root 2. So that means that this component is square root 2 divided by 2. All right, so we have r dividing by 1/2, same thing multiplying by 2 over 1, and then we have square root 2 divided by 2. So sweet, 2's cancel, and we get r is square root 2. So for sure. I'm sorry I had to jump through so fast, like confirming that. But yes, like, could you prove that both these angles are the same? I think after watching these videos, sure, that was very rough. But I don't think you should be able to, visually you should be able to, sure, these are both 30, but prove it. You know what I mean? From this video, you'll be able to do that. So hell yeah, in this video, if you know two things about a right triangle, you know everything about it. But hell yeah, this height is going to be square root 2 of the radius. But nothing is drawn to scale. I mean, this should be 60, but we go over all that. So hell yeah, it's a long one, but we go over a hell of a lot of the fundamentals. So that was the short solution in under 5 minutes. Leave a lot of likes and let this, just keep this looping on your computer for 24 hours. All right, hell yeah. All right, hell yeah. So at a viewer's request, this was a problem. And so I just printed it off how they wrote it in the comment section. But with this, I was able to copy this into Google and actually see a picture of it. Because on this one, like I think, like sometimes the written problem, like part of that is actually determining what the problem looks like from what the person said. But if there's a confusion, then that's not useful. So I did look up a picture, and so it was what I thought it was. So we have a spherical balloon, and so I can just draw this balloon up here. And we have a radius of r. Hell yeah. And then subtends. See, I don't even know what that means. But it's this angle from like where you see the top. So you're going to be down here on the ground, and you're like, oh, there's the top of the balloon. Cool, that's right there. And I should draw this a little steeper. So hell yeah. So this is a 60-degree angle. Don't look like 60, so let's get it to be 60. There you go. So hell yeah. So you, an observer on the ground, that's going to be right at eye level. Booyah. And we're going to say this distance is negligible. So this is kind of, we're going to call this the horizon. Maybe you're down in a hole. You know what I mean? Sweet. Looking at that balloon up there. All right. And and this is 60 degrees. Let's read on. At the eye of an observer. Cool, we did it. And we even made the observer in a hole, so the eye of the observer is on the level of the ground. That was pretty sweet. If the angle of elevation of its center is 45 from the same point. So we're going to say, hey, here's the center. And then here is the angle to the center. Cool. I'm just going to continue this line just all the way. It might as well. If it's a circle, we're going through the center. We're going to hit 2 other points. Maybe those are useful. Okay. All right. So then prove that this height, booyah, right there. The height of the center of the balloon, yeah, it is square root 2 times its radius. Oh, wow, okay, so we have a balloon, you know what I mean, that's kind of strung to the ground. Maybe we got, we probably got a row of cars if we got balloons out, like an auto dealership. All right, hell yeah. So, you know what I mean? Come to the auto dealership, get your car. All right, sweet. And, yeah, so I guess that's it. That's this height, eh? Hopefully I read that right. And then how do we prove that? Well, so I think, and then the question, like making these videos is just like, well, isn't there a fundamental that like we should just all know? Or like what are the fundamentals that hopefully we always know? And that's where I always point them out, try to in every video. I never try to gloss over those fundamentals, because it's from those fundamentals that we're going to be able to answer like harder problems. And so so I would say with this falls into the category of a trigonometry problem. So the one that I'm going to write first, because I always forget it, is if we have a triangle, Pythagorean's theorem, a squared plus b squared is equal to c squared. Sweet. And check it out. Like even right here, hey, this is the height. This is one of those sides. So like now we've just broken it down. And then so that's the other thing. Like I graduated college. I've kind of mentioned this couple of videos of like, hey, we want to have equations and we want unknowns. You know what I mean? So 1, 2, 3. This is one equation and 3 unknowns. We need 2 more equations. If we're going to solve for b, we got to get 2 more equations. And we can't get any more unknowns if, you know what I mean. If we still had a total of 3 equations and 3 unknowns, we'd be able to solve for b. So I think that is kind of a fundamental also. All right, but let's go back to geometry. What do we know about geometry? So here's my kind of take-home point, is that if you have a triangle, right? And if we, like, the most important thing we know about a triangle is, of a right triangle, we have a right triangle, is the angle. And this is not elementary. And I always have to, I did not know this until last year. It wasn't so obvious to me. That obviously, if this is the right triangle, this is 90. And for the life of me, I couldn't go back to 8th grade and say, oh, a triangle is made up of 180 degrees. And so we have a theta, we have a 90, and then so that means that this other angle, we can call it, sometimes I do this, just a box for, I don't know, but in this case, our other angle, you should get into the habit of, maybe calling it phi. This is theta, that's phi. But check this out. So this is going to be plus phi. But with this, sure, we got two unknowns. It looks like we got two unknowns. But if I do know this angle, so let's just say, hey, this is a 30-degree triangle, what does that mean? That means that by this relationship, which always existed anyway because it's a right triangle, it's like, this is like one of those equations where it's like, it's nothing new. It just like this equation is nothing new. It just kind of spells it out that sometime in a problem, you're like, okay, I know this side and I know that side, and then you're just like, huh, am I stuck or something? Or you just forget that, oh, this is the definitionally a right triangle is defined by this ratio of these two sides. When you square them and then sum them, is going to be equal to this other side, the hypotenuse squared. Cool. Now that's the same thing that's going on here. So if I have a 30-degree triangle, well, guess what? We know that that is 60 degrees. So sweet. And this is what they call complementary angles. It says that two angles, add up to 90. That's the definition of complementary. Supplementary, this happens a lot too. It might happen in our problem. It's like, hey, check this out. This is supplementary. So these are the basics that no one's going to go over because they might not be useful to the problem, but they're all components of trigonometry that are at its fundamental so important. And then here, anytime that you're doing trigonometry, I'm going to go over a couple things at once. Hey, make another coordinate system. And then so let's go over this idea of supplementary. Supplementary says, hey, see this line? I know this is 60, so guess what? I know this angle because 180 degrees is equal to these two angles, 1 plus 2. And so that's going to be 60 plus, oh, I don't know, we can call this alpha. And so 60 plus alpha, hey, I know what alpha is. It's 180 minus 60. And so just knowing one, you know the other based on this idea of supplementary. Hey, this is like another one of those equations where it's just like, I don't know, does it add anything new? Nah, but if you know this angle, it's just like, well, no, duh, you already know the other one. All right, so I think that is useful too. All right, and then with trigonometry, hell yeah, look at this. So see how we have this is horizontal. Hey, this line is also horizontal. This is the concept that these two lines are parallel. But hell yeah, this angle is the same as that angle. I don't know, so maybe that's going to be useful too. That's 60 degrees because, hey, this angle down here, we're just going to pop it up right there and try to figure out something. But anyway, I think this little guy is the most important. But that's just one of the two things that we know. Okay, so hell yeah. So that's the framework. That's the easiest things. That's like saying, hey, I have a triangle. It's made up of 180. I have a right triangle. These two angles are the same. That's all we've done so far. The other element of a triangle, a right triangle, is if I know two things about it. So let's say I know this angle, and I know one other thing about it. You know what I mean? And I just want to take a pause. Let's say this. Let's say I know both these angles. Well, no, that's not two things. We already just spelled out that if you know one, you know the other. There's no new piece of information. So this is not knowing two things. So that's the only slip up that you can make in this kind of word statement that I use, that, hey, if you have a right triangle and you know two things, I know an angle and a hypotenuse, I know everything about it. It's because we know how a right triangle is related. We know how this side is related to the hypotenuse because we've defined an angle. And it's so fascinating that, hey, if I have, this is my xy axis, and I just make a line. Hey, that's an equation. Maybe it's y is equal to 1/2 x. So we have over 2 up 1. So this is the only line from this equation. This is the only line that can be made. You change this, you change the equation. You steepen this slope, you steepen the, so I don't know why I think this one is weirdly powerful to me, just because, just the other week, I was just like, oh yeah, no duh. Is that any line that has a slope is related to an angle. So this slope is related to this angle. If I change this slope, I have changed this angle. So, booyah. And I think this is useful because, hey, look at this. This slope is 2 components. And this is not trivial, because another commenter was just like, hey, vector space. He was doing linear algebra, and he's like, isn't this just all a mathematical abstraction? And I was just like, damn it, it is, yes. And I was thinking about that this year, is like, wait a minute, I actually had that aha moment. Hey, I'm adding vectors, I'm doing the cross product, doing the dot product is useful, opening a door, that's going to be a moment, torque, all that stuff. And then I was just like, what was I like? I was just like, what is, like when you add, what was I thinking? Like when you add vectors, yeah, you're like, why? Yeah, why do vectors add a certain way? Yeah, oh, that was it. Like why when I just have this chunk of mass floating in outer space and I can put a known force on it, like why does it go that way but not any other direction? That should seem trivial, but like why isn't it not unstable? Why isn't it not like that classic problem that's getting millions of views, is if you have something on a dome, you know what I mean? And then you impart, and then some sort of movement happens. It goes from 0 velocity to some sort of velocity. Well, there's an idea that it could take any path. So even just like right here, why is there just absolutely no components? Why does this behave like vectors? Why is that useful? I don't know. That's the question. That's just like, and I guess the answer, I don't know what the answer is, but it's a good question to ask. And then is the answer just, solving more things that are similar, like building confidence in something, like having a number system 1, 2, 3, stating that there's an equal gap between all of these, but is there? No, I'm just joking. But yeah, it's like even like that, it's just like cool. But this is a mathematical abstraction, but it's going to be particularly useful as we get used to it and then just always do it a certain way. But hell yeah, this falls into the term of linear algebra, adding vectors. Like this side, A plus B does not equal H. But there is a relationship. We can square this and add it to the square of that, and that is. So it's just the nature of two things that are 90 degrees apart, don't influence each other. But still, if I put another force here, F prime, it's as if I got rid of both of these and then put a force like at a 45 degree angle. If both of these are the same force, it's the equivalent of taking the square root of 2F and then just applying it there. So that is significant. And that you can do by observation. You know what I mean? And so if that's the case, then this idea, but still like, I don't know what came first, the mathematical abstraction or just the fact that all of those things in that abstraction are related. The fact that, hey, this triangle, I can treat this as a radius of a bigger circle. And so when this comes in, this component this is going to be less than the radius because I'm dropping down perpendicular. This is the radius. If I went to the radius here, I'd go all the way to the edge, and then I'd have kind of two separate triangles. A radius, and then a drop down and two perpendiculars. So, hell yeah. I don't know. All right, so that's enough. That's enough of that. But anyway, so back to reality. And I really like geometry because, but let's go over. So yeah, you do have this idea that if I know this angle and I know this hypotenuse, I know this side. I know the magnitude of this side. I know the magnitude of this side as a number. And we just have this charted. You know what I mean? We say that, and you could look at it as a circle, but anyway, we just know that, hey, if I draw a horizontal line and then come up at an angle and make it a magnitude of 10, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then I have this angle, let's say 30. That means when I drop this down, and this is perpendicular, I go measure this. You know what I mean? It's going to be 1, 2, 3, 4, 5, and this is going to be 1, 2, 3, 4, 5, 6, 7, 8.6. You know what I mean? So if this is 10, I measure this at 8.66, and this is 5. And cool. And it's just, it has to be that way. If I have a horizontal, and then I have a hypotenuse, and I have it at some sort of slope, and then I drop down a perpendicular line, that these two lines have to be what they are. Because we just said that, you know, if I have this, if this line is, this slope matches this angle, yeah, so that's where we're back to. So that's why this is a very useful way to show slope, because this also, it doesn't show you the angle, but it shows you what it shows you what the sides could be. Because that's the other thing. That's the only, I did say that if you know two things about a triangle, you know everything. But that's not, what's not true about that? No, I think that is true. Let me double check. Yeah, hell yeah, that is true. Because right here it looks like, well, I know theta and I know theta, but these two triangles have different sizes. Yeah, because you only know one thing. You only know one thing about this triangle, and I mean this is particularly useful. Like this is more information than you just know the base. If you just knew this base right here, then this is all you could draw of the triangle. But if you knew this angle, hell yeah, you could do something like this. You could be like, hey, I know the triangle, the right triangle is going to be somewhere along here. But if you just knew the base, then all you know is like, hey, this is the base, and the triangle could be a small angle to there, or it could be a hella big angle. But this would have to be perpendicular. So let's go up all the way to the top of the page. And yeah, if this is still perpendicular, you could have an angle that's close to like 89. But yeah, so this is when you know only one piece of information about a triangle. But if you just know the angle, that's particularly useful because now you can see how this is scaled. Like, and in this case, this might be 2, this might be 1, and if that's the case, then this is 2 squared, which is 4, plus 1 squared, which is 1. So this has to be the square root of 5, which is the same. Now I could just, let's say this is just, this length is double, so this is 4. Well, cool, everything is just proportionally bigger, so this is 2 square root 5. So that's the case when you get something like this. Like I'm not worried about a unit triangle because I can always come up with that mentally later, but I do know that this is square root 5, and that's one skill to be able to do quickly. Hey, this is 2, this is 1. Well, obviously, let's talk through it. This is 2 squared plus 1 squared. Take the square root of that, that's this side. So 2 squared is 4, 1 squared is 1. Adding those is 5, so square root of 5 is going to be that side. Now we're kind of interested if the hypotenuse is 1, that's significant. Because if I get the hypotenuse of 1, then these sides are literally percentages in the sense that, hey, like let's say this was 0.5 and this is 0.866, my hypotenuse is going to be 1. because this is the square root 3 divided by 2, and this is 1/2. Let's do this. Let's square these. So we have 1/2 squared. So I bring this, this is the same thing as squaring the 1, squaring the 2. That's an important mathematical thing that, can't be understated. If I square this whole thing, same thing as squaring the top, squaring the bottom. Because then it's just, we're easy, cheesy. This is 3/4. This becomes 1/4. 3/4 plus 1/4 is 1. Square root of 1 is 1. So that's particularly useful for a unit. If you get this down to a unit, but you can do that after the case. You know what I mean? I can find the percentage, or the percentage of, if this was 1, what's the percentage here? Well, it's just 2, this length, divided by the hypotenuse. So that is identical. So let's do that. So we have this square root 5. We have 2 and 1. How do we make this a unit triangle where this is 1? Well, we had to do that by just dividing by the square root 5 here, and we have to do that on all sides. So that is a unique property of triangles and vectors, is you can, and it's the property of scaling. So if I have vector f, force f, you know what I mean, that's, and in this case it would be, and its magnitude is square root 5. Cool. And so we have 2 pounds of force, or 2 newtons in the I direction plus 1 newton in the j direction. All right. I don't know where I'm going with that, but oh yeah. So let's say I'm just like, well, I know this is a square root 5, but I want to divide it by the square root 5. I just want to take this vector and divide it by the square root 5. Well, cool. And these components. So I would write vector f is equal to f of x plus, f of y. I took a vector and divvied it up into 2. And I'm just kind of on this kick of like linear algebra because someone's question. Because linear algebra blends into quantum mechanics very seamlessly. And it shows you how, like, hey, we can do things in 3 dimensions with Cartesian coordinates and even show that. But you can just add extra 90 degrees. So we have 3 things coming in 90, and those 3 things are 90 degrees to each other, so they behave in this property. If I put a force on one, it's going to go that direction. It's not going to go this way, and it's not going to go in and out of the page. So that property is unique, but we still have an equation that can be an amalgamation of a bunch of those properties, and you can still reduce it to kind of one vector. So that's kind of the anyway. All right, so hell yeah, I guess I was just saying that we can take this and divide it by the square root 5, and that's just dividing its components by the square root 5. So yes, is this divided by the square root 5 is just this divided by the square root 5. All right, hell yeah. So that's kind of intro to a geometry problem that I do, because if I want to know the percentage, and this would be the cosine. This is the angle theta. I want to know the cosine. The cosine of this angle theta is the percent of the hypotenuse in this direction. So if the hypotenuse is 1, then it's just this ratio, which is 2 divided by the square root 5. So I can just do that fairly fast. Or I can do this triangle, square root 5, 2, and 1, and then divide by the square root 5 everywhere. So this becomes 1, this is 2 square root 5, this is 1 square root 5. Now this is a unit triangle where the components are percentages, and when you square those percentages, and when I say percentages, I'm always talking about a fractional of a whole. So 0.5 is synonymous with 50%. So if I draw this to scale, this is 1, 2, and now I have a triangle that's 1, 2. And so, well, let's do a sine of 30. So if I have this is the fastest way to do a 30 degree. Do a 90, do an arc, and then you can easily divvy up this arc into 3. Booyah! So that's a 30 degree. So if I have this is going to be 1/2. This is going to be 0.866. So this is going to be 0.5, and this hypotenuse is going to be 1. So the percentage of this length is 50% of the hypotenuse, and I can even visually see that. My trick is to always take your hypotenuse and then at least divide it in 2 and see if any of those sides are similar. Hell yeah. And then sometimes divide it into 4 if it's, you know what I mean? Hey, look at this. So we would have 1, 2, 3, 4. And this would be a right triangle where this would be a 1, 1 to 4. So this is 25%. Now, is this 75%? Hell no, because if this is 4, this looks like 3.98, you know, or very close to 4, however that works out. So this is almost 100%. All right, so that is going to be trigonometry in a nutshell. I think we can start this problem. All right, booyah. So let's draw our balloon, the center, and then we're going to draw that 90 degrees. To this point, I guess, and then we're going to come, and this is going to be perpendicular, so we have 60 degrees. Again, here's my head, and we got a little hole. And from this same eye, you know what I mean, hey, I can see X-ray vision through the middle of the balloon, and this is 45 degrees. So the trick with geometry, I don't know if this is a hard problem. I don't know if it's easy or hard. I have no idea. But the cool thing about geometry problems is, like, I don't think they can be impossible. I don't know. Maybe they can be, where it's just like, whoa, it's like a puzzle to put it together. But you're just trying to make right triangles. That's useful. So hell yeah. We even came up with our first right triangle, and we even labeled it. This was square root 2r. Is that what it says? Prove that the height of the center of the balloon. See, this is where, if I did this problem, I would say prove that the height of the center of the balloon from the horizontal, or I don't know. But I guess, like, yeah, they're not going to say what's the elevation of the balloon from the bottom of the balloon. That would just be the radius. So sometimes I have to even say, like, well, could this be any other way? The height of the center? You know what I mean? Is it measured the opposite direction? You know, hell no. Is it the height from the surface of the moon? No, it's just the height from the surface of the ground. There's no other location that would make sense. So yeah, there you go. So pretty confident square root 2r. So here's our right triangle. Here's 45. Oh, and check it out. What do we know about right triangle? Is that, hey, this is also just square root 2r. But let's not do that. Because I like to work to the hypotenuse and then back to the side. Because to get this relationship between this and this, you have to use tangent. But I'm going to show that, hey, tangent of an angle is just sine of an angle divided by cosine of an angle. And I'm going to show you that this is a corner that you shouldn't cut until, well, I should cut this corner more because just to get familiar with it. I can't tell you that this is, this, like the thing that I don't know, is square root 2r tangent of 45, or is it tangent 45 divided by the square root 2r? I don't know. But I think I came up with this idea that if this is the opposite and I want to find the adjacent, you know what I mean? I mean, we could spell it out. So tangent of 45 is equal to the opposite over the hypotenuse, which is square root 2r divided by the thing we don't know. So cool. So and I want to know this thing, so let's take this up there and bring that down. So cool. So yes, this thing that we don't know, this side, is going to be square root 2r divided by tangent 45. But let's show you the process where we don't use tangent, and we use, well, this is still kind of a trick. So I know that if I knew the hypotenuse, that this would be a percentage of the hypotenuse. So the hypotenuse, always the bigger number. I'm going to take a percentage of it. Let's say 50% of a large number is going to be half of that number. And that's going to be maybe a component. In this case, you should know that a 45 is 0.7 over here and 0.7. It's 0.707, but basically 70% of whatever the larger number is, the hypotenuse, is this length. All right, hell yeah. So how do we work backwards? If I said, hey, this larger number times 0.7 or 70% is the smaller number, you know what I mean? How do I get this number? Like, I know this. I know this one and I know 70%. How do I get that? Well, it's just an equation. Just rearrange it. So I'm going to say, hey, this larger number is this number that I know, this side, divided by 0.7, which is square root 2r divided by 0.7. So here's how I do it from a intuitive perspective. I know that this angle, I'm going to put some sun shining rays on it, is associated with the sine. So if I say sine of 45, what does this mean? It's a percentage, or it's a fraction. It means that if I knew the hypotenuse, let's say I just know the hypotenuse is a larger number, and then I knew the percentage of this side of the hypotenuse. I don't know if I'm scrambling my words, but the sine of 45 is a percentage. So anytime I see sine or cosine, let's say it says cosine 45, well, that's a percentage of this related to the hypotenuse. So if this hypotenuse is 10, this is about 7. I can just see that. If I make 10 hash marks, 1, 2, 3, you know what I mean? Divvy this up into 10, I can do this. 1, 2, 3, 4, 5, 6, 7, about 7. Cool. You know what I mean? So always do that with geometry. Because especially if you don't know, if you're typing into your calculator sine 45 and you're clueless about what's going to pop out, this is where you would do that. You would be like, well, it's not going to pop out 7, it's not going to pop out 10, but if I did, cosine 45, which is this, it's going to pop out the percentage of this length to the hypotenuse. So if I said the hypotenuse is 10 and this is 7, I'm going to have 0.7. And so I say percentage, it's a fraction of a whole. So 7 divided by 10 is 0.7, which is synonymous with this is 70% of 10. Cool. If I took 70% of 10, which is 0.7 times 10, and it's just, hey, this is an equation. We got 3 things. We can rearrange these any way we want. So bring the 10 upstairs. 0.7 times 10 is that side. All right. So here is the trick. I know that here is the angle. Sun is shining. This is the sine component. So I know that sine of this angle is related to these 2 things. Cool. So I'm going to write that in. Sine of 45 is a percentage of these 2 things. I know that, bummer, I kind of messed it up. How I like to, I've spent, 4 years in college just being like, hell, I want to know the hypotenuse. So if I know the hypotenuse, I take a percentage of it, that is going to be like this side. That is how I think of sines and cosines. So if I take the hypotenuse and multiply by the sine 45, this is this bigger number times, 0.7, and that's going to give me the length of that side. Cool. When you scale down this triangle, like let's say you divided everything by 10, so I would have square root 2r divided by 10, square root 2r divided by 10. Well, now I have a unit triangle where square root 2r divided by 10 by definition has to be 0.707. You know what I mean? If this is a 45-degree angle. And the sine of 45, yeah, it has to equal 0.707. You know what I mean? Where, if I scale this up by 10, that's going to be indicative of the hypotenuse times sine 45 is that length. So I use that as the foundation of my wheelhouse, that if I know the hypotenuse, the larger number, and I multiply by the percentage, which is hypotenuse times sine of the angle, or hypotenuse times cosine of the angle, that gives me the length of the other side. So if I do the opposite, I'm going to take this side, which is square root 2r, and now I want to do something to it to get the hypotenuse. Well, I'm going to do something with it with sine of 45 because this is related. So what do? Do I multiply sine 45 by this? Or I can do 3 things. So that's going to be the first thing I could do. I could take square root 2r divided by sine 45. And I guess I could take sine 45 and then divide it by the square root 2r. So let's talk about all 3 of these. If I take this number, which is a smaller number than the hypotenuse, and multiply it by a fraction between 0 and 1, which is, let's say, 0.5. That's smaller than 1. So a smaller number multiplied by a smaller number less than 1 gives me an even smaller number, which can't be the larger number. The hypotenuse is always the larger number. So this is, obviously the answer is this, but let's see how this one's not the answer. If I take this smaller number and then divide it by a larger number, what do I get? Well, I get an even smaller number than this number, for sure, so this gives me a smaller number, so that can't be the hypotenuse. But this one, it takes this side, which should be the smaller number, divides it by a fraction, which is a smaller number than 1. I guess, it's not smaller than, doesn't have to be smaller than this, but it's smaller than 1. And so any number divided by, this number divided by 0.5 is the same thing as that number divided by 1/2, which is the same thing as that number multiplied by the inverse, which is 2 over 1. So in whatever numbers, this could be 0.35. I could take a number divided by 0.35. Always do this. This is a good mathematical skill. Take the denominator, turn it into a fraction. 0.35 divided by 1. Don't do that. That's not going to help you at all. But anyway, because you can't, you don't, unless you can get that as a fraction, it can make mathematical sense that you're multiplying by the inverse. If you can get it into this shows that, hey, dividing by 0.5 is the same thing as multiplying by 2. I think that's straightforward enough. All right, so we did enough juggling there. Let's do it in fast action. If I know this side and I want to know the hypotenuse and I know this angle, it's going to be square root 2r divided by the sine of 45. So there's 3 things to know. You need to write. I'm still taking this, and then I'm doing what? Well, dividing by a smaller number. And is this smaller number going to be cosine or sine? Well, it's going to be sine because this is the angle the sun is shining on the sine component. Cool. And then so how about this? Let's say I have this, square root 2r, and I want the hypotenuse. Well, same thing. I'm going to do cosine 45. I got to divide by a smaller number to get that hypotenuse. And this is related to the cosine of that angle. All right, hell yeah. So anyway, that's kind of my introduction to, that was the second introduction to geometry. But, how else are you going to do geometry problems if you don't have a thorough foundation? And I think this foundation, sure, this is the stuff that you might not know. But if you're doing harder and harder problems, this is what happened to me in college. It's just like, I'm doing a harder problem, but I think I got left behind on some of those basics. I graduated college with never using square roots as fractions. I never wrote square root 3 divided by 2 ever. And that's just because our university was equation-based, answer in the back of the book driven. Nothing wrong with that. You know what I mean? It's because it gives you maybe a more down-to-earth reality perspective of hey, we just want to build something and not kill people. You know what I mean? So we still have a fundamental understanding of what's happening, but we're not going to win any mathematical awards and competitions, because we need our calculator to make sure we didn't mess up. But now going back, it's just all this stuff is super useful. And geometry is wild because it's just hey, if I know a triangle, there's 3. That was the thing that I wanted to do this year. I wanted to learn more about the trig identities, but in time. I wanted to do problems that were if a trig identity popped up, I wanted to then explore it because it was a practical thing. But doing that, then I was just okay, I got it. Because trigonometry had the basics, and then they had all these identities that seemed like it was an endless possibility of complex things that I would never understand. But now I can see that, hey, there's a limit to that. I guess there doesn't have to be a limit to the complexity of trigonomic identities, but just for the most part, I can now have a grasp of, hey, there's an end to that alley. You know what I mean? You could learn everything about that. Cool. All right, so let's do it one more time. All right, hell yeah. So I think we're getting faster. So now we're going to start drawing right triangles. That's kind of the general most important aspect. So head height. I'm going to be in a hole. And from here we got a 45. So hell yeah, we're starting to draw it fairly accurately. This is perpendicular. Okay, so that's a right triangle. And this is a right triangle. Probably just need these two. Like, I don't know. Who knows? But we got square root 2r. Alright, so now, and I'm going to use, I'm probably, the one thing that I'm for sure going to use is if I know two things about a triangle, I know everything about it. So hell yeah. So that's, don't need to stutter. Slow down. Alright, that's how I can play the game without, writing a bunch. So if I just get this problem, I can be like, cool, 60 degrees. I can start checking off things that I already know. Like, instantaneously, I should be like, well, I at least know that angle, so that's a check mark. Okay, 90, 60, 30. Cool. And then if I know this side and an angle, that fits that mantra. If I know two things about a right triangle, I know everything about it. So I know this side. That's going to be, I should start in the order that I would do things. We just said, hey, I know the hypotenuse. Cool. And you can just now visually say that. It's going to be square root 2r divided by sine 60. So this is square root 2r divided by sine 60. Dividing by that smaller number gives you that larger hypotenuse. Once I know that larger value, I know that that's that larger value times cosine 60, and that's that. So those are the prereqs for geometry. I would practice that skill of, and then, I don't know, I think it's harder to go this way to that way, but this is just one thing I threw into my wheelhouse this year. Else, you just go back to 8th grade and be like, it looks like I know an angle, and I know an opposite. So let's just start writing them all. Sine of an angle is opposite over hypotenuse. Cosine of an angle is adjacent over hypotenuse. And then tangent of an angle is opposite over adjacent. What am I interested in? I'm interested in the hypotenuse. So it's got to be one of these two. At least we narrowed it down. And then what do I have? I know the opposite. I don't know the adjacent, so it has to be this one. And then, so this is very important, because even just going back to this stuff this year, I was just like, oh, I didn't realize that. Like, I only see this equation in one direction, or just like, hey, I use it this way. I know that sine theta is opposite over hypotenuse. Maybe I can see that inverse sine of sine theta is equal just to theta, and then that would be inverse sine of opposite over hypotenuse. So maybe I can see that theta is just inverse sine opposite over hypotenuse. But, before that, I could not see that, this is one equation with three terms that I can rearrange in three different ways. So I could say, hey, I want to solve for the hypotenuse. Get the hypotenuse upstairs, drop sine theta downstairs. So hell yeah. And it looks like we got another equation. So I could say this is one equation. This is two equations. They're the same equations. They're not new equations. But hey, we got one more. Let's solve for the opposite. So I would have to get the hypotenuse upstairs. So we got opposite is equal to hypotenuse sine theta. And this is typically the one that I always use anyway. I always want to know the larger number and then multiply by sine theta, because I know it's a fraction of that hypotenuse. It's a percentage of the hypotenuse, and that's going to be the smaller number. So, but we're doing the opposite. We know the opposite, and then we know the sine of this angle, because we can throw that into our calculator. And intriguingly enough, yes, we just know this from tables. We just know this from tables and calculators. You could know this from a Taylor series. Do the Taylor series out to like at least five terms, and maybe you can get within, maybe 6 terms to probably get within 3 decimal accuracy. I don't know. Depends. I'm just hypothesizing on that. But hell yeah. So that's just the nature of it. And it's back to, hey, this angle is associated with this line, and it can, and if I make a triangle out of it, I have to drop down a vertical, and then there's just a relationship between that length and this length. And that's always going to be the same. If this angle is 60 degrees, this smaller triangle will still have that same percentage. This will be the same percentage as the hypotenuse. And out here, you can see how you can just see how it's scaled, and it doesn't change that ratio. Alright, hell yeah. I hope this one goes pretty easy, because I feel like this has been a pretty good video so far. Even though, you know, it's classic of mine just to be like, hey, I'm going to go over the things that no one... Why I go over this is because no one reiterated it for me. And then you just think that math and physics is tricks, and then, hey, if I knew the equations, I can get to the unknowns, but, head scratcher. How do I get the equations? And then all problems are just like, okay, like, hey, like you have this concept. This is where like harder engineering classes are going to be easier, because you have to use very specific equations. But then you'll get these problems where you're using like two very specific equations. Let's say it's just sum of the forces in the y equals sum of the forces in the x. And then you're just like, well, what links them together? And then it's just like this very simple, you know, geometrical, like it just has to be. Like if you have a geometrical formation, it's just like, well, no, duh, those have to be there. And so it's that equation that trips you up. Like, you know those two, but then it's always finding that third equation that relates things. And it's just like, it's because no one spends time to reiterate that, you know, exactly what I just did there. This equation, well, that's three equations. They're not unique to each other, but both, if you don't see this as three different separate equations, then you're missing the power behind this relationship. All right, cool. So if I know two things about a triangle, I know everything about it. All right, so moving on. So now I know that, and damn it, I messed up. So this total angle is 60 degrees. So, yeah, it's going to be, so let's see. Yeah, hopefully, and then I'm just going to go over here. This is 45. So that's a bummer, because everything I was talking about this being 60 was dead wrong. I mean, well, it didn't have to be. I could say it was 60 degrees. As it was on paper, it was 60 degrees. And if I was saying it was 60 degrees, it was. But it's not representative of a problem. This angle right here is 45. So everything still applies, that this is going to be square root 2r divided by sine 45. And so I don't think I messed up. Like over here I had it as 45. I just, yeah, so the third time drawing this picture. So there you go. This is 60 and this is 45. Oh, this is going to be genius if we get to use, because today I made a 10-minute video on the sum of two angles and the difference between two angles. So let's say I have two angles. This is theta, this is 15. That's synonymous with this is 60 and this is 45. So hey, what's this angle? Well, this angle is going to be 60 minus 45. So I'm just going to write that in. So we have 60 minus 45. But again, I'm doing things like right now that this would be extracurricular. Like everything up to this point is like foundational. But this would be like, ooh, that looks like a trick. You know what I mean? Just the fact that, hey, if I wanted to know, if I knew this length and I wanted to know like the sine component, this height, then I could use this relationship. I'm sorry. If I wanted to know, if I knew this hypotenuse and I wanted to drop this down and do this as a right triangle, this would be a hypotenuse and this would be a right triangle. So maybe I want to know this sine component. But at least we can talk, at least we can do that. You know what I mean? That's a very important concept of trigonometry, to be like, hey, look at this. Treat it as a hypotenuse. It might not be a hypotenuse, or this is a hypotenuse to this triangle, but cool. Let's make this a hypotenuse to this triangle. Same thing. We're going to lay down that horizontal. We're going to say that this is our hypotenuse. And then if this is the horizontal, we're going to drop down a 90. And now I have, this is my angle. And so this is the angle, 60 minus 45, which is, this would be a 15-degree angle. So I have 15 degrees here. I don't know. Let's just say this is a distance of 500 feet. And so I have 500. I could figure out this distance if I wanted to. That's the cool thing about geometry problems, is like you can do whatever you want. You know, I mean, it might not be helpful to get to this height, but it at least goes through the process of your confidence. And this is I would consider this more advanced, but hell yeah, if you know any sort of length, you can turn it, and you know an angle to something else, you can drop it down, make a 90. You can make that right triangle and then find that component and that component. All right, so now we will see if there is any quick way to get to that answer. All right, we are running out of juice on this battery, but all right. So and it's getting kind of busy, but let's go back to it. I know this angle and I know this side. I know everything about this triangle. I just said that I know this angle is 60 and this is 45, so I know this angle is 15 degrees. And then I just said that I know this hypotenuse, so I know everything about this triangle. And this has, I drew a right triangle here where this is the hypotenuse, but check it out. This radius comes in, and this is just something you need to know, that if you have a circle and you have the radius, a tangent to it will always be perpendicular. And this is the definition of a tangent. We are looking at the farthest molecule. So if I'm looking up in the sky, and, oh, sweet, I just have this little circle. So if you are, I don't know how to do this, but if you are looking down at this, you're probably seeing this point. You can't see this point, theoretically, if it's a spherical balloon. You know, you wouldn't be able to see my pen until I brought it to maybe like right there. So this point, if I actually made a black mark on it, you might see where any point that's obscured behind it, you won't be able to see. But this point that you see with black marker, the first place that you see that, is not synonymous with halfway. Well, in this case, it's not. Yeah. In this case, I think the stating the obvious is that you can't see the top of the balloon. That's all I was getting at. You can't see the top, so you're seeing, you know, someplace down the balloon. So yeah, we're going to keep that in mind. All right, hell yeah, let's see if this problem's doable. So we have this right triangle, so we just said that we know everything about this triangle right here. And we know its angle. But the wild thing is like, sure, we know what this length is. Oh, check this out. And we're doing the problem in reverse. So we're actually just saying that we know this, but we don't. This is an unknown. Because I was just like, oh, this is really easy. So this is a tactic that I use. It's just like, hey, are you trying to find this angle? We'll just say that you know it. You know what I mean? And if I know it, then I know, and I know this angle. That doesn't change. So I know everything about this triangle. And then I come over here, I know this angle. So that means I know everything about this triangle. Well, that means that if I know this radius. You know what I mean? So that's fascinating. So I could even prove this problem in reverse. I could say, hey, let's start here, get the hypotenuse, and it's going to be, you know, something with the radius. And then I can know about this triangle, 15 degrees, and then get this, which is the sine component of 15. And that would give me the dimension of the radius. And if the dimension of the radius turns out to be 1/2 r or 3r, well, then I did the problem wrong. But then if you go in the original order, so let's draw this again, because we're almost there. I'm going to throw in a new battery. All right, hell yeah. So I think we got our solution. So let's draw it big as. So we have our balloon. We're going to have our 90 degrees. It's pretty close to 90. We're going to have 45 degrees. Well, I should have done 45, so if 60 was right there, we're going to be right there. But yeah, let's draw it to scale. So hell yeah. So there's 45. We have, this is hitting tangent to the circle, so we have a 90 right here. This is the horizontal to the ground. Huh, the balloon's not very high. But hell yeah, so this is our observing head, and we're in a hole. And we're level with the horizon. Alright, booyah. This is R. So now I'm going to say this is 60 and this is 45. But let's just write it like this. This is 45 and then this is 15 degrees. And that keeps it nice and crispy. So now we can use that. I wanted to go into more detail on like why if I have a triangle and I know these two things, the angle and a side, or if I have a triangle and I just know A and B, these two sides, then I know C, and then if I know that, then I know the angle. You know what I mean? Because it's charted. You know, every triangle is charted. If I know this side and this side, I know the relationship between these two sides in a chart or using a Taylor series. I know that angle. It has, the same thing as just like if I do the line and I have this slope, this is A and this is B, it has to be synonymous with this angle. If I change B plus 1, this angle for sure changes by some quantity. It has to by definition. So, yeah, just the nature of a right triangle. I don't know. It's just like, that's where it's just, I don't know what a proof is, because I can just do simpler ways of explaining it. But I think kind of looking at, this was kind of cool. The equations for sine and cosines, these three equations, have three different things. Two are lengths, and one is an angle. So it seems like, oh, that spells it out. It's just like, well, don't you need to know three things? Well, no, because this says that if I know two things, then I know the other thing. There's only three variables in here. So if I know two of these variables, I know the other variable. But that's where if I know theta and phi, well, that's dumb, because that's just 90 is equal to theta plus phi. That's just that's not new information, and we went over that. All right, so hell yeah. So we're going to go from this approach. This is our radius. How do we get this height? So we're going to say, hey, I have a length and I have a degrees. I know two things about this triangle. I know everything about it. So I know this side and this hypotenuse. Cool. Now I come to this triangle. I know the hypotenuse and I know this angle. Cool. I know two things about it. I know everything about this triangle, and this is what I'm trying to find. So that is how you do this problem in a very short amount of time. But now we're going to go through and run it through with the numbers. This 15 degrees, I can approximate that sine of 15 is just sine 30 divided by 2. All I'm doing there is saying that sine 15 is the same thing as sine 15 degrees, and then divided by 180 degrees in pi radians. And so this is equivalent. This would be sine of, this would be very similar to sine of 0.25 approximately. And then I would say this is small angle, and I would just say sine of this is just equal to 0.25. So that's how small angle works. That's how, if you have sine of 30 and you just know it to be a half, that it's linear. So sine 15 is approximately 0.25. Sine 7.5 is approximately 0.125 or an eighth. All right, but I think just from my knowledge, 45-degree triangles, 60-degree triangles. So this one is juicy because we can use. So maybe we can. So yeah, if I use the functions of sum and difference of two angles, then I can say that maybe I'm overcomplicating this. But yes, how do I get this 15 degrees in terms of this 60-degree triangle? That would be interesting. I even might pause the video. I don't want to because but yeah, obviously, let's do it the fast way first and then see if we can get there or not. I mean, the fast way just said, hey, what are we trying to find? Well, if I knew this hypotenuse, that would be sweet. I know the opposite. So I'm going to say I'm going to take r and then divide it by sine 15. This is the hypotenuse. So then I'm just going to treat this as a hypotenuse. Now what am I going to try to find? Well, I'm going to try to find the side. I'm going to take this hypotenuse and then multiply it by sine 45. So hell yeah. And then this is this. So and this is a check marks. That's not an R. So this is just the things that I know because I know two things about a triangle. So hell yeah, that's that. So this is the answer. But now the question is how do you prove that it's square root 2? So this is where in my calculator, just to make sure I'm not making horrible errors, is I do sine 45 divided by sine 15. Now let's slow down because sine 45 is 0.707. As a decimal, I know this is a decimal. Like I said, I stayed away from square roots, but I do need to know this is square root 2 divided by 2. Cool. And then I just said sine 15 is approximately 1/4. So I'm going to have square root 2 divided by 2 divided by 1/4, which is the same thing as square root 2 divided by 2 multiplied by 4 over 1, which is going to be 2 square root 2r. So then prove that the height of the center of the balloon is square root 2 times its radius, square root 2r. Why am I getting 2 square root 2? So let's maybe slow it down and see if I made an error somewhere. Maybe with my sine of 15 approximation. I said sine of 30 is a half, so sine 15. Yeah, I'm getting a different answer than this. So maybe yeah, I mean, maybe it's one of those problems that just has an error. That happened last time. Students just like, hey, can you solve this problem? And the answer in the back of the book was just, they were just solving like an inverse of something. They were just solving like they changed values around. All right, so fundamentally, if I know this is the opposite, so sine of this, if I knew the hypotenuse, let's spell this out. If I knew the hypotenuse times sine 15 is r. So the hypotenuse is r divided by sine 15. This is the hypotenuse. If I know this hypotenuse, I know this opposite side. Because if I know this opposite side is, I'm just going to say that, is equal to the hypotenuse sine 45. So then this side right here is going to be r divided by sine 15 times sine 45. Okay, now I'm just going to type it in my calculator. Sine 45 divided by sine 15. And we get 2.73, which is, and are we in degrees? Sine 45 divided by sine 15. And that's square root 2. Why did I think? Yeah, square root 2. What? Oh, no, I'm getting 2 square root 2. Yeah. So 2 square root 2 is approximately what I get. Which is, so sine 45 divided by sine 15, and that's 2 square root 2. So that's it should be exact if that was the case. All right, bummer, man. Do I have to re-look at this problem from a different perspective? I'm going to take a pause on this because obviously something is going on. Alright, hell yeah. So we messed up the problem and because we did not know what subtends mean. And I looked it up and it's like, hey, if I have a circle here and I have this angle, then this arc is subtended by this angle. So this arc, to hit right there to the edges of this arc, I hit there, and so that is subtended. So let's draw this how it's supposed to be drawn. But that's cool because we did our problem 100% right. Everything that I said that's why I was so bizarre. I was just like, I wonder what I am getting wrong. If because the logic that we just showed there is this was true. So I was just like, what gives? And so this angle is 60. So if I take, which is bizarre because like I have to take this pretty steep. So I'm going to take a steep angle, right? Because it's 60. Yeah, you really can't even draw it to scale. That's kind of a bummer. But yeah, let's just, even if it's not drawn to scale, I'm going to get... Alright, we're right there. And so subtended means like, hey, I'm going to hit this side of the balloon and then this side of the balloon. And that is going to be 60 degrees. So obviously it's difficult to draw because that is not a 60-degree angle. So it's for sure not to scale, but we would have to be pretty darn close to the balloon. Okay, so we have that. And now it says, so we still have the horizontal. We're still in a hole. And then the angle of elevation of its center is 45 degrees from this point. So this angle, is 45. So there you go. So this angle is 45 degrees. And this angle to there. This angle is 60. And if we, yeah, so this whole angle is 60, and this line right here chops it in half because we have a radius here and a radius here. Let's see if by definition these two lengths have to be the same. Well, obviously, if I'm an observer and I'm looking at two corners of the sphere, I could look directly into the middle of the sphere, so I'm always kind of in line with the center of it, and if I look equally on both sides, then yes, these two lines are going to be the same. Because this distance from my eye to the center is the same, and these radiuses are the same. So just by definition, what we were talking about for trigonometry, I know this. I know this length. Let's say I did know this length, and I know this side of the triangle. I know everything about this triangle. I know this angle here, and I know these two sides. Cool. Same thing here. If I knew this length, and I knew this was the radius, I would know everything about this triangle. As said, so that said, I know that this triangle right here is going to have 30 degrees, and this triangle right here is going to have 30 degrees. Here's my 90. So let's point out our hypotenuse. These are the components, because these are the 90-degree angles. This is the hypotenuse. All right, sweet. And then we have this third triangle that drops down. This is a 90, and this is the height that we want. So, like, we can do the same thing. We can work backwards. That's a good method. Let's say I knew this height, and it's going to be square root 2r. Let's do that same method. So if I know this height, do I know anything else about this right triangle? Hell yeah. I know this angle is 45. So we can play that same game. I know this is the, I know the hypotenuse for sure. And then, cool, if I know this hypotenuse, do I know, and I know this angle, I know everything about this triangle. So I know this. Cool. All right, so, so we played the game in reverse, so now let's play the game forward. I know this angle of this right triangle and a side. That means I know everything about this triangle. I know this side, I know the hypotenuse. If I knew the hypotenuse, cool. The hypotenuse is a component of this right triangle, and I know its angle. So I know two things about this right triangle. I know everything about it, so I do know this height. All right, so let's work from there, and I bet you we can do it fairly fast. So let's get the hypotenuse. That's going to be this component r. What are we going to do to it? This is our angle. It's a sine component. We're going to divide by sine 30. And the reason we are is because it's going to be a smaller number. It's going to give us that bigger hypotenuse. And just in general, if this is 30 degrees, you know, you should probably know from a triangle, like, hey, this hypotenuse is just twice. Whatever this hypotenuse is, 30 degrees, this is just half. So, like, right there, this is 2r. Like, you could throw that in if you wanted to visualize that. But just from an equation-based way, we said, hey, I know this, divided by sine 30, now I know my hypotenuse. Sometimes it's useful to throw this in brackets, because now this is the hypotenuse, and we want to know one of its components. So that's like taking that hypotenuse, a larger number times the percentage, which in this case we know the angle, so that's going to be sine 45. So I'm going to take this hypotenuse and then do sine 45. Hell yeah, and that is going to be this height. All right, so sweet. So it's just, the only tricky part about this problem was you had to figure out what the hell subtens mean. Subtends, I'm sorry. And I did not know. And that's the hardest thing for me about, what do you call it? I mean, I guess you don't call it English if it's, what do you call reading and writing? Like just words? Yeah, words are hard for me, man. I don't know their meaning. And I just pretend like I do. If I don't know a word's meaning, I'm just like, oh yeah, sounds like, you know what I mean. But when it comes to, I need to, that's like red flags. Every problem that I've gotten wrong from this perspective is because it had a word I didn't know, and I just said, I just got rid of that word. I don't want it. I just said a spherical balloon of radius r. There's an angle of 60 degrees from the eye. Like, why the hell would you measure it from any other place in the ground, but in this case you're measuring it from there and there because you make this special little problem. All right, so what we just did is got an equation for this height. I'm just going to do that, and hell yeah. So I can say h. This is the height h. So cool, sine 30. So we have r divided by sine 30 is a half, and then sine 45 is square root 2 divided by 2, because sine 45 is 0.707. Double this, what do you get if you doubled it? That's going to be 1.414, which is synonymous with sine 45. So that's why this is really useful to know the 3 digits. All right, booyah. So cool. So that's and then if you took 1.414 divided by 2, well, you would have square root 2 divided by 2, which is 0.707. So that's how those are related. So sine 45 is square root 2 divided by 2, which is that 70%. And you should always know this first is 70%, second if I'm teaching it as this 3-digit decimal, and then third as the square root 2, just because that's the, I mean, if you do know it like this, and cool, square root 2 divided by 2. That's what's been burned into your brain, but I don't see anything here. I just see, but you could say you do see something. This is the one more thing on trigonometry. Is that, cool, this is an angle, but when you take the sine, you're always getting a ratio. So sine of an angle is a ratio. So I do like to write these equations like this. Sine of degrees, because this is the units of an angle, degrees is equal to a ratio. Even though a ratio is unitless, and even degrees are somewhat unitless, like radians are kind of unitless. But anyway, so sine of an angle gives you a ratio. How about inverse sine of a ratio? Well, hell yeah, that gives you degrees. So that's an important relationship. And why I say that is because we just did sine 45 and we spit out, like you should say, a ratio. And if this is a ratio of what? Well, let's go back to our just generic angle, and we did the sine. That's a ratio of this opposite over hypotenuse. So we have square root, so I can just draw a triangle that says 45 degrees. We're going to have square root 2 and 2 right here. And let's draw it one more time just a little nicer. So we got 45 degrees, right triangle, square root 2, 2. And now never forget about Pythagorean's theorem. And it's, you might know it this way. A squared plus B squared is equal to C squared. And in here you might have to write it like variable A squared plus something I know squared. Square root that is equal to 2 squared. But you should be able to do this also fast in reverse. If I square the larger number and subtract the square of the side, so yeah, this side, A, is the square root of the larger number, 2 squared, minus square root 2 squared. And so this is one of those equations, is just like A squared plus B squared is equal to C squared. Cool, we know it, because now I can see that C is the square root of A squared plus B squared. But let's say I want to find B. So B is equal to C squared minus A squared, and then the square root of that. And so this is one of those that for sure I threw in my wheelhouse just this year to be like, hey, I need to say that on a dime. So if I don't know this side, hell yeah. It's 2 squared minus square root 2 squared, square root that. And we have 4 minus 2 square root. So we have square root of 2. So that is what we have right here. So this triangle is square root 2, 2, and that just makes sense. Hell yeah, but that comes from this ratio. That's why that's here. Same thing with 1/2. What is this? Well, we just said it's this side divided by the hypotenuse. And the hypotenuse is 2, this side is 1. Or that ratio. So that's the ratio of those sides. All right. Hell yeah. And then, so we got it. So the height is going to be r. So this is 1/2. Same thing as multiplying by its inverse. So we have height is equal to r. Dividing by a half is the same thing as multiplying by 2 over 1. So we got that. So we have r. 2 divided by 1, square root 2 divided by 2. The 2's cancel, and we have the height is square root 2 r. But, you know what I mean? I mean, I messed up because I didn't read, and I think this video is totally necessary, especially if someone's like, how do you do this? Well, why it was so easy, because I went through the entire fundamental of geometry, and if someone's not going to go through that fundamental every time that you have a geometry problem, then you're going to get trapped in this idea of like, oh, just kind of guessing, using a couple of these equations. But the wild thing about trigonometry is just like this equation can be written 3 different ways, and that's difficult to see. And that's just one equation. We got 2 other equations that are also relationships, and so and then there's 3 different ways to write that, and that's just trigonometry at its basic. That's not even dealing with anything fancy. So hell yeah! So I think we did it. We really nailed home the idea that if you know 2 things about a triangle, you know everything about it, and then you can just move on to the next right triangle. So, hell yeah, I think I'm done with this one. But yeah, this is a standalone video and a worth watch. So, thanks for joining me. And it was so cool that I messed up, you know what I mean? I didn't know that, hey, if I'm looking at this subtended, hey, it's out in space, means from maybe edge to edge. So if this is the arc that I see, and that makes sense, because if I look at a balloon and I only see like a wedge, and we should actually draw this to scale, because that was driving me crazy. Like, what's a 60-degree angle? So the easiest way to draw a 60-degree angle is to do this, divvy it up into 3. So hell yeah, that's a 60-degree angle. So now I can just say, hey, the balloon, now I'm just going to draw this 30. So I'm going to put this as my radius, and I'm going to go out perpendicular. So sweet. Now I can actually draw this thing to friggin' scale. So there's the balloon. Now I'm at a 45. So what I do here is I come here, and then I drew my coordinate system. Same thing, come in here, and maybe just divvy it into half. I think that's a fairly decent way to crop out a 45. And what they're saying is that, damn it, that these 2 points are the same. So, yeah, that's a bummer. I have to rotate this. So if I rotated this degrees, about to there, then hell yeah. To the horizontal to me now is this, and this is horizontal to me, and then if I do this, this is about a 45. So there you go. Ooh, this one is tricky as hell to draw, but at least we did it. And let's see if I can draw it one more time. So I have this. We're for sure going to draw the 45. And, yeah, why is that so tricky? Well, and then we don't have to get too fancy, because we know everything about this. If this is 45 and this is 30, this is 15. So, I don't know why I'm losing my mind drawing this thing. But, yeah, let's draw it one more time. So we have... a balloon. Oh, I shouldn't have drawn the balloon. Alright, bummer. Alright, so we have our observer in the hole. We have the horizontal. So and this is good, because this is a good way to draw angles. I like this method. I drew like a sun shining arc, and then I divvy it up into thirds. You can always divvy it up into half later. But if you divvy it, you got one opportunity to divvy it up into thirds that you can visually see that it's thirds. And then I come in and divvy these up into halves. So this is 60, this is 30, this is 15. And if you wanted to divvy this up into thirds, hell yeah, you would do 2 marks, and then you would have 5, 10, 15. But hell yeah, so we wanted that 15 degrees. And so there was one. We wanted 45 degrees right in the middle. And then we wanted another 30 degrees from 45, which 45 to 60 is 15, and then here is another 15. So there you go. So, and obviously this makes sense now. Doesn't matter where the balloon is, because it's friggin' huge. I mean, I guess it could be really far away, but just really big. I mean, this is why. So the balloon's either monstrous and not very far off the ground, or just fairly close. So, hell yeah. And then we're going to do perpendiculars to there and there. And that distance I don't know. You know, I mean, you can just, this distance is going to be the same, and we got some points to hit our balloon. Ooh, that was, after all that, it's like a square. All right, sweet. So we got our balloon in there. And subtended 60 degrees. That's 60, because here's 90, and there's 15, and there's 15. So it's 90 minus 30, that's 60 degrees. And we got this 45 degrees, so we drew it. Hell, that was difficult to draw. All right, so hell yeah, subtended, and that's what I was getting at. This arc has to be a certain arc length. And do we know that? Hell yeah, that's a better question. And what's this arc length? Well, you know what I mean? After all that, why would I come to this question and then just scratch my head? You know what I mean? We don't need to do that because we got this. We can say, okay, I know this angle is 30. Guess what? I have a right triangle here. I know everything about it. Also the complementary angle. I only needed to know one thing for that, but hell yeah, that's going to be 60 degrees. Same thing over here. Here's 30, so this is 60. So this is a 120 degree sweep. So if I have this arc is subtended of the angle of 120. Or I don't know how you say it. I'm just trying to get used to this word subtended that I got so hung up on, and that kind of ruined the problem. But this was pretty... Alright, so my camera cut out, but that's it. So yeah, this word subtended sucked, and but we figured it out. But yeah, it was fascinating, because I even kind of looked at a picture, and I was just like, oh, okay, the balloon's up in the sky, we got some angles. How hard could it be? But yeah, it all hinged on that word subtended. And we learned a little bit. So booyah. So I got to be done. We're not learning anything more. But it was very cool to draw angles. We got to end it at that. Oh, and that's, before my video cut out, yeah, that's a real take-home point. Is like, how do you draw some angles? Do this arc, divvy it up into thirds, because you can visually see thirds. So hell yeah, that's 30. That's 60. You know what I mean? And then divvy it up into halves. We for sure have the 45s, but this is 15, this is 75, and then just put 2 more hashes, and you got 10 and 5 degrees. And you have 10 and 5 degree accuracy all along this arc. And then hell yeah, then pick another point, and then do the same thing. You know what I mean? If you have another angle, you know what I mean? Do this, thirds, maybe you got a 60 degree, come up here, and then maybe you got a 45 degree down. That's simple. Alright, sweet. Thanks for joining me on this one, and guess what? That's a video.